Okay, let's go ahead and take a look back at this problem. So again, what the issue we're running into is, actually there is no issue we're running into. The network is working. It shouldn't actually be functioning this way per the RPF check. So what's happening, router 7 is sending multicast traffic over to 3. 3 is sending it down to 1, 1 is sending it down to 2. Okay, that's based on how we had our PIM network built. Okay, we saw that that was previously working when we wanted to send traffic from router 7 all the way out to router 8. Okay, so 7 is sending the traffic to 3. 3 sends it down to 1. 1 is sending it down to 2. Okay, 2 is informing router 4 about the source through MSDP. Then router 4 is sending a join message, a PIM join message up to 2. A 4 then forwards the traffic onto 5. 5 forwards it onto 6. 6 is forwarding it out to 8. Okay, when the traffic is received on router 5, it is doing a lookup in its IP routing table to see what is the incoming interface for the multicast packet versus the outgoing interface for the unicast route. Okay, when router 5 looks at its table, it sees 2 routes. It sees one through router 1 in BGP and then one through router 4. Now, router 5, RPF failure actually should be occurring on router 5 now. So what I'm going to try to do, let's block this advertisement from 2 sending it out to 4 so that router 5 only has one route to the destination. Let's have it route just through router 1 through BGP. Okay, so let's look back at the command line. And on router 2, we're going to block this advertisement from going out to router 4. So what we'll do, there's a question here, what does the show IPRPF on router 5 show? It doesn't show anything because it doesn't have a multicast route to the source. If we show IPRPF 10.1.37.7, it says we don't have an RPF entry for the source. Okay, that's because we don't have a static multicast route and we don't have any multicast BGP learned information. So this is what the problem should be, but it's not actually occurring on router 5. So let's go to router 2 and let's shut down the BGP peering between router 2 and router 4. So under BGP 123, we'll say neighbor 151.24.2, actually let's just filter out the advertisement. Let's say route map, no routes, deny 10. And then as we advertise stuff out to router 4, we'll apply this route map on to effectively just deny every advertisement out. So we'll say under BGP 123, as we're sending updates out to router 4, we'll apply the route map, no routes, outbound. And we'll clear IPBGP outbound. Okay, so if we look at router 4 and we show IP route BGP, we see 10.1.37.0 is reachable via 150.1.15.1. Okay, so it says we need to go up to router 1 to reach this, and if we look at the next hop, show IP route 151.15.1, this is via router 5. Okay, so let's look at router 5 now. Show IP, let's clear the multicast routing table, then show IP mroute count. Okay, no traffic is getting through yet. Let's see if router 7 is still sending. It's still sending. And actually, the RPF failure may be occurring on router 4 now. Let's say show IP mroute count. Okay, we receive 444. Let's see if this is incrementing. Okay, so router 4 is not receiving the traffic now. Let's see if 2 has it. Show IP mroute count. Okay, let's go ahead. Let me clear the multicast routing table everywhere, and then we'll start with a new start a new transmission on router 7. So clear IP mroute asterisk. Okay, so now on router 7, we'll go ahead and ping to, actually before we do that, let's go ahead and join the group on 8. Okay, so on Fast Ethernet 6, we'll say IP IGMP join 224, we'll say 10, 10, 10. Okay, so router 7, we're going to send traffic towards 224, 10, 10, 10. It's going to go out Fast Ethernet 03 from 10.1.37.7, which is our interface address. Okay, so this traffic should be getting up to router 2, show IP mroute 224, 10, 10, 10, because this is the rendezvous point for our own autonomous system here. Okay, we see the source comma group entry for it. It says the outgoing interface is null. So router 4 is not sending a join message up to router 2. So let's show IP mroute 224, 10, 10, 10. We can see that it says the incoming interface is the serial from router 5. Let's take a look at router 5. Show IP mroute 224, 10, 10, 10. Says it's coming in null from router 1. RPF neighbor is router 1. Let's look at let's see if router 4 received a source active message about it. We'll say show IP MSDP SA cache. Okay, so router 2 did send a source active message. So router 2 told router 4, I have the source that's sending to the group. Okay, RP is 150.1.2.2. The peer is 150.1.24.2. Okay, so what actually is happening here on router 4? If let's debug IP M packets, debug IP PIM, and debug IP MSDP peer and routes. Okay, what we should see here is that router 4 is not going to send the message. Let's get rid of the rest of these groups that the neighbors are joining. Okay, so we'll take this join message off, and then we'll go ahead and reapply it on router 8. So IP IGMP 224, 10, 10, 10. If we look at router 4, we received the join message from the neighbor, but we're not forwarding this up to router 2. So if we look in the MSDB cache, we can see that we're learning this from router 2. We're learning about that source. it says the RPF peer is router 2, saying peer RPF check passed for single peer. We're accepting that advertisement, but we're not forwarding the join message up to, router 2. We can see when the traffic gets to router 2 is just going to be dropping the traffic. Let's debug IP-m packet on router 2. We should see router 2 receiving it, and then no, it's not receiving. Is logging on? Show log. Console logging is on. Okay, let's make sure router 3 is receiving it. Debug IP-m packet. Okay, so router 3 is receiving the traffic, but it says the outgoing interface list is null. Okay, the reason why is that the RP has not requested router 3 to build the tree towards any destinations. Okay, router 3 knows about the source, but it doesn't know that there are any destinations in the network. So it's receiving the traffic and it's just dropping it. Okay, the reason why is that router 3 registered the source with router 2. Router 2 is sending a register stop message back saying, I know about the source, but at this time I don't have any clients that are joining it. So go ahead and just don't send that traffic to me until I request it later. Okay, let's say on router 4, let's try this. In global config, we're going to add router 2 as a default peer. Okay, we're sending a join, but we're sending the join to router 5. Let me make sure. Oh, I think I know what the problem is. Let's say show IP-PIM RP mapping. No, we have ourselves as the RP. Let me make sure that we're not running PIM on that interface between router 1 and 5. Okay, let's go ahead and let's take a look back at the diagram here. Now, I don't want to spend too much time troubleshooting this because it's actually not broken in the first place. We can see that the traffic is passing through router 5. Now, a better design for this would be actually router 1 and 3, and you can see that there's an example of this in the technology labs for multicast. If we had router 1 and 3 inside, let's say, AS13, router 5 and 6 in AS56, and then router 2 and 4 inside AS24, and we were running multicast routing along the same path that we have now, but we were running unicast routing between AS13, AS56, and AS24. And let me go ahead and set this up because I want to show you guys how to see when the RPF failure is occurring and then what you can do in order to prevent it. Okay, so let's go ahead and change the BGP topology here. What I'm going to do also, we'll take our PIM sparse mode off the interfaces and we'll just replace it with dense mode, so we're flooding the traffic everywhere. Okay, so we're gonna run PIM along the same interfaces that we have, but we're gonna separate the BGP autonomous system. So between 1 and 3 we'll have AS13, between 5 and 6 we'll have AS56, and then between 2 and 4 we'll have AS24. Okay, so on these interfaces here, let me start at router 6. Go into gigabit 01. We'll say IPPIM dense mode. Okay, so with the dense mode configuration, we don't need to worry about MSTP because we don't have any rendezvous points. We're just gonna flood the traffic everywhere throughout the network. Okay, then on router 5, same thing. So on Ethernet 01 and serial 00, we'll run PIM in dense mode. So on router 4, no router BGP 456. On serial 00, we'll run PIM in dense mode and Ethernet 00. Okay, then lastly on router 3, so no router BGP 123. Let me undebug that multicast traffic. Then on the Ethernet to router 7, we'll run PIM dense mode, and then we'll run dense out towards router 1. Okay, so on router 1 and 3, we're going to run BGP 13. So we'll peer over to router 1. Okay, and on router 3, we're going to advertise this prefix, the link to router 7, into BGP. Okay, so far we're running just unicast BGP. Okay, on router 1, we'll go ahead and run BGP as well, router BGP 13. We're going to peer over to router 3. We're going to peer with router 2, who's going to be in AS24, and we're also going to peer with 15.5, who's going to be in 56. Okay, so 3 different autonomous systems we're dealing with, router 1 and 3, router 2 and 4, and then router 5 and 6. Router BGP 24. We're going to peer with router 1 and router 4. 4 is going to peer with 2 and 5, 45.5. 5 is going to peer in BGP 56. We're going to peer with router 1, who's in 13, and then router 6, who's in 56. And router 6 is going to peer with router 5, 56.5. Okay, then we'll advertise this other endpoint, network 10.1.60.80, into BGP here. Okay, so let's look at the BGP topology. If we go to router 5 here, we'll say show IP BGP summary. We should see peerings up with routers 1, 4, and got on router 4. BGP 56, we're going to peer with router 4. Okay, so if we look in the BGP tables, we can see that those two networks, the network on router 7 and the network on router 8, are propagating end-to-end. So we should have connectivity now between router 7 and router 8, basic unicast connectivity, 68.8, okay, which we do. Now, if we trace the route to this, we see it goes from 3 to 1, from 1 to 5, 5 to 6, and then 6 to 8. If we look at the diagram, we can see the reason why this is happening is that when router 5 does a lookup on the route in BGP, it's going to see I'm learning this route through AS13, and I'm learning this route through AS24. Okay, so when comparing the AS path, we're going to see 13, then we're going to see 2413. So we're choosing the route through router 1, which is going to be based on the shortest AS path. Okay, now for the multicast topology, multicast is running on the links, let me draw this out here, between 3 and 7, 3 and 1, 1 and 2, 2 and 4, 4 and 5, 5 and 6, and then 6 and 8. So when we do the lookup on router 5, we're going to see a discrepancy between the unicast route to the source and the incoming interface for the multicast traffic. Let's take a look back at the command line. And on router 8, we'll go ahead and join a group. Okay, now since we're running dense mode, we don't need to worry about any type of rendezvous points. As soon as we join the group, we're going to have a dense graphed message that is sent everywhere that is adding this interface to the multicast routing table. Okay, then when we go ahead and send the traffic out from the source, it's going to be flooded out everywhere. And since this join message is occurring, we'll say IP-IGMP join. Let's do a new group. We'll say 224.20.20.20. And then from router 7, we'll go ahead and send traffic to this. 224.20.20.20. Give it a high repeat count. Interface is going out fast Ethernet 03 from 10.1.37.7. Okay, if we look at router 3 and we look at the multicast routing table, show IP mroute 224.20.20.20. Okay, it says it's coming in the Ethernet. We're sending it out serial 1/2. We're sending it out as dense. Okay, so we're just flooding it out that interface. From 3, it's going to go down to 1. 1 is receiving it in the serial. It's sending it out the ATM as dense. Show IP mroute 224.20.20.20. Okay, we can see we're receiving it in the ATM, sending it out the Ethernet. When 4 gets it, show IP mroute 224.20.20.20. We're receiving it in the serial and forwarding it out the Ethernet. Okay, so this is not correct. Router 4 says that the RPF neighbor is router 5. We should be receiving it in the Ethernet. If we look back at router 2, router 2 says it's coming in the ATM and it's going out the Ethernet. When router 4 is looking at it, it says it's coming in the serial link and it's going out the Ethernet. Let's go ahead and do a lookup on the unicast source here. Let's say show IP route 10.1.37.7. It says it's reachable via BGP from router 5. So when router 4 is routing to the destination, it is routing out through AS56. Okay, so now we see a problem in the topology. The incoming interface for multicast is the Ethernet to router 2, but the outgoing interface for the unicast route is out through router 5. Okay, this is because we're preferring here on router 4, we're preferring our external route over our internal route. So if we said show IP BGP 10.137.0, we see we have two routes. Okay, one of them is internal, one of them is external. Okay, actually, the reason is a different reason that we're preferring it. If we look at the next hop value here, it says that I don't have a route to the next hop, 150.1.12.1. Okay, router 4 does not know how to reach that destination. So if we, let me go under OSPF, we'll take the passive interface command off. No passive Ethernet 00. No passive Ethernet 10. Now you can see as you start to combine all of this stuff together, you get a lot of complexity that is built on top of each other. So unless you're building the network in a structured fashion, testing your layer 2 configuration, testing your layer 3 routing configuration, then once you get later into the exam, something like multicast, if you're trying to troubleshoot multicast configuration and it's related to something in your basic layer 2 or layer 3 domain, then you're going to have a lot of wasted time in your troubleshooting process. Okay, you need to make sure that you're verifying all of this stuff on a task-by-task basis as you are building the network first off. Okay, so if this was the exam, when we were building the BGP, when we were building the BGP information, we should have noticed that we didn't have that correct IGP routing in order to build BGP on top of it. Okay, so we can see now when we look at router 2, traffic is coming in the ATM and we're forwarding it out the Ethernet through multicast. So if we look at router 4 now, let's go ahead and look at the multicast routing table. And now it says it's coming into Ethernet and going out the serial. Okay, this is correct. Okay, so the reason it was looking the other way before, it said it was coming in the serial and going out the Ethernet, was because when we did a lookup on the source, so router 4 said show IP route 10.1.37.7. This was reachable via router 5 on the frame relay link, on the serial link. It should have been reachable via router 2 on the Ethernet. And when we looked at the show IP BGP output, or show IP BGP for the prefix actually, we saw that we were choosing router 5's route over router 2's route. And it told us that because we didn't have a route to the next hop. It said that this was inaccessible. Okay, but looking at this at a very high-level overview, we should see that based on the AS path information, we should not have been routing through router 5. Okay, so just by looking at the topology from a very high-level overview, we should have seen that that was an error somewhere in the routing path. Without manipulating any attributes, we should be choosing whatever the shortest AS path is through the network. Okay, so if we look at the multicast routing table on router 5 now, we say show IP mroute 224.20.20.20. It says that it is the incoming interface is null, outgoing interface is the Ethernet, and the outgoing interface is the serial. Ethernet 01, this is the link to router 6. Serial 0/0, this is the link to router 4. If we look at the debug IPM packet output, we should see router 4 flooding us the traffic. Actually, we may have to clear the routing table here because router 5 is going to be sending a prune message up to router 4. So let's say clear IP mroute asterisk. And when you get into this troubleshooting process, you can see that convergence is going to have a lot to do with it. Let me see if I'm logging to the console. Okay, we are logging to the console. Debug IPM packet is on. We look at these interfaces. We have no IPM route cache. Show round interface Ethernet 01. No IPM route cache. Okay, let me try clearing the table on router 4. And let me send this to all of the devices at the same time. So from the access server, I'll say send star clear IP mroute asterisk. Okay, this will send it to all the TTY lines that are attached to the access server. Okay, so now we can see we received the traffic in from router 4 in serial 0/0. Destination is 224.20.20.20. It says RPF lookup failed for the source. This is not the RPF interface. Okay, so the reason we weren't getting these messages before was because with dense mode PIM, if we do not want the traffic, we're going to prune it back up to the source. So 5 was sending a prune message to 4, 4 passed the prune message up to 2, to 1, to 3, etc. Okay, by clearing the multicast routing table, we're reflooding the traffic at the source, which was router 3. Then after this failure, then router 5 is going to be sending the prune message. Okay, so this can be kind of hard to troubleshoot because it depends on what point in time are you looking at the debug information. Because you could look at this debug and say, well, router 5 is not receiving any traffic. If we look at the debug on router 4 is not going to be receiving anything either. Okay, we could see it was flooded out again densely. Okay, once it was flooded, router 5 is going to reprune it again because it's not sending it out any interface. Okay, so the problem is if we look at the routing table on router 5 and we say show IP route 10.1.37.7, this BGP learned route says it's reachable from router 1, and router 1 is reachable out Ethernet 0/0. Okay, so the outgoing interface for the unicast route is Ethernet 0/0, but the incoming interface for the multicast traffic is serial 0/0. So now, based on that these are not the same interface, we have an RPF failure, and router 5 is dropping the traffic. Okay, now where multicast BGP comes into play is that on this path, we can selectively choose where we want the RPF check to happen based on multicast BGP information. Okay, so what multicast BGP is going to be used to do is propagate the source advertisement solely for the purpose of doing the RPF check. Okay, so it's going to be similar to doing static multicast routes, but it's going to happen dynamically through BGP advertisements. Okay, it is enabled through multi-protocol BGP, just like IPv6 or VPN v4 is. Okay, so we're going to go into the address family for multicast. We're going to activate the specific peers that we want to exchange multicast information with. Then we're going to advertise the multicast sources into the BGP multicast address family. Okay, so if we look at the diagram here, we have unicast routing that is following this path. Let's say that the unicast traffic is green here. Okay, so the unicast traffic flow is in that direction, but the multicast traffic flow is in this direction. So what we need to do between routers 2 and 1 and between 4 and 5, actually basically we're going to do it between everybody, but AS13 is going to exchange multicast information with AS24. AS24 is going to exchange multicast information with AS56. A router 5 and router 1 are not going to exchange multicast routes, multicast BGP. So multicast BGP is going to follow the path that PIM is running on. Okay, running multicast BGP does not take the place of PIM. PIM is still used to send the join messages and the prune messages on a hop-by-hop basis through the multicast network. A PIM is always going to have to run end-to-end. But multicast BGP is going to be used just to override our RPF check to make sure that the multicast traffic can flow end-to-end. Okay, so it's allowing our unicast path to be different than the multicast path. Okay, so let's take a look back at the command line here. So first thing, we're going to start on router 3. And under the BGP process, we're going to enable the address family IPv4 multicast. Okay, now we're already peering with router 1. We're just going to activate them for this address family. So we're going to say neighbor 151.13.1 activate. Okay, under this address family, I am going to do a network origination for 10.137.0/24. Okay, so it's a separate advertisement from my IP version 4 unicast advertisement. We're advertising this network into unicast BGP and into multicast BGP. Okay, now on router 1, in BGP, we'll say, in multicast, we want to exchange multicast information with router 3, and we want to exchange multicast information with router 2. Okay, on router 2, router BGP 24, we're going to exchange multicast with router 1 and with router 4, 24.4 activate. And now keep in mind, just like the VPN v4 address family, the attributes in BGP, things like next hop modification, communities, route maps, filtering, all of that stuff is going to be on a per address family basis. So the problem we had before with the next hop lookup on router 4, router 4 was doing a lookup on a unicast BGP route, and it didn't have a route to the next hop value. If we fix this with the next hop self command on router 2, we would have to do it for unicast BGP, and we would have to do it for multicast BGP. Okay, so it would be two separate commands under the different address families. And router 4 will say, in BGP 24, we want to run multicast with router 2 and with router 5, 45.5. And on router 5, neighbor router 4, activate them, and activate router 6. 56.6, oops. 56.6, activate, and we can see now the multicast traffic is flowing. Okay, let's finish it on router 6. Technically, router 6 doesn't need to run it because it only has one path. The unicast path would be the same as the multicast path. But for consistency, we'll go ahead and enable this on router 6. Okay, so we'll say neighbor 151.56.5 activate. Okay, so if we look on router 5, where the problem was occurring in the first place, we'll say show IP BGP summary. We can see for unicast BGP, we're exchanging information with routers 1, 4, and 6. We say show IP BGP IP version 4 multicast summary. We can see we're exchanging multicast information with router 4 and 6. We're not exchanging multicast routing with router 1. Okay, we can see we're learning a prefix from router 4. We say show IP BGP. We have our unicast route coming from router 1. If we say show IP BGP IPv4 multicast, we have the multicast route coming from router 4. Okay, so when we receive the traffic in, we're not going to look at the unicast table to do our RPF check. We're going to look at the multicast table. So on router 5, if we say show IP RPF 10.137.7, says this is known via multi-protocol BGP, which is multicast BGP. The interface that it comes in should be serial 0/0 because the RPF neighbor is router 4. Okay, so now when we look at the debug IPM packet output on router 5, we can see that the traffic is flowing. Okay, any questions on multicast BGP? Okay, next thing we're going to take a look at here is a configuration known as Anycast RP. Now, Anycast RP is going to be an intra-AS multicast technology. Okay, so we're not going to be using Anycast between BGP autonomous systems. We're going to be using it inside one autonomous system. Now, what the goal of this is to provide redundancy and load balancing between our rendezvous points inside one single multicast domain. Basically, the logic is that our rendezvous points are going to share a loopback address. Okay, so let's say that we have the loopback address 1.2.3.4. We're going to assign that to multiple devices in the network. So multiple routers are going to have the same IP address assigned. Okay, when they run IGP, and the devices, the rest of the routers in the network do a lookup on the destination 1.2.3.4, they're going to route to whatever the closest device is that has that address assigned. Okay, that's going to be based on whatever our IGP metric is. So if we're running OSPF, we're going to look at what is the OSPF cost to get to 1.2.3.4. Whatever the closest neighbor is, that's where the traffic is going to go. Okay, what this means is that when I send a PIM join message, or when I send a unicast register message, it's going to go to the closest RP in the network. That's going to be based on the IGP metric. Okay, now when we do this, we're going to run into a design problem. The situation we're going to have, let's look at the diagram. Okay, we have router 2 and router 4 as the rendezvous points. Okay, this is all inside one autonomous system. We have them inside BGP AS100. Okay, on router 2 and router 4, we assigned some loopback that's the same. We'll say it's 1.2.3.4. Okay, we assigned loopback 1, 2, 3, 4. We advertised it into IGP. Now we have a multicast server that came into the network. Okay, router 7 is sending traffic into the network. When this traffic comes in, it's going to go to the designated router, which is router 3. Router 3 is going to send a unicast register message to the rendezvous point. Okay, router 3 says the rendezvous point is 1.2.3.4. Based on the physical topology here, the closest Anycast RP is going to be router 2. So that register message is going to get to router 2. Router 2 now knows about the S(G) entry. It knows what the source is, and it knows what the group is. Okay, now router 8, it says, I want to join this group. It sends an IGMP join message up to router 6. Router 6, on a hop-by-hop basis, sends the PIM join message upstream towards the rendezvous point. Okay, from router 5's perspective, the closest rendezvous point is router 4. So router 4 knows about the star(G) entry. Router 2 knows about the S(G). It knows about who the source is. The problem we run into is the same problem we had with inter-AS multicast, which is router 2 knows the source, router 4 knows the destination, but they're not communicating the information between each other. Okay, the way we solve this is that between the Anycast RPs, we run MSDP. Okay, so in this case, MSDP is used as an intra-AS multicast technology. Now the configuration is really straightforward. The only thing we need to do is advertise those loopbacks into our IGP. Okay, everyone is going to say this is the RP address. We can either assign it statically, we can assign it with AutoRP, we can assign it with BSR, however they want to do that. Okay, but the key is everyone has to agree that the RP address is that loopback. Okay, then router 2 and router 4, they're going to peer via MSDP. So when they receive a join message or a register message, they're going to exchange those source active messages between each other. Okay, so let's go ahead and set this up real quickly, because this design, this is going to be the basis for the final example for today, which is going to be multicast support inside of MPLS VPNs. Okay, so everything we've done up to this point so far, it does not relate to MPLS. This is just when we're routing regular IP version 4 packets inside the network. Okay, there's a question here. Is it always via IGP or via iBGP? You mean the Anycast RP advertisement? Okay, you could do it via BGP if you wanted to. Just typically inside your own network, you're typically already going to be running IGP. So if not everyone is running BGP, then the easiest solution to get that advertisement out would just be to advertise it into IGP. But if we wanted to, we could go ahead and set this up into BGP. Like, let's say we'll make router 2 a route reflector for router 1 and 3. And we'll make router 4 a route reflector for 5 and 6. Then we'll configure an iBGP peering between 2 and 4. Okay, then we could advertise it into BGP, and they would choose, based on the IGP metric to the next hop value, what is the closest neighbor. It would be kind of redundant in that case, because they're still using IGP in order to do the next hop lookup. Okay, so in our case, we're just going to run IGP and then advertise it into the network. Okay, but the key here is that this is inside one BGP autonomous system. Whether or not these devices are running BGP, they're within the same network control. So it's not an inter-AS technology. It's an intra-AS multicast. Okay, so first off, let's get rid of our BGP configuration, and let's make sure that we're running IGP on all of these interfaces. So say no router BGP. Okay, so we got rid of our BGP configuration. Let's make sure that we have OSPF end-to-end now. So let's show IP route OSPF. Okay, and we do. So if we trace, let's say we trace 150.166 from 150.133. Okay, so we can see we have end-to-end reachability there. We have reachability from router 3 all the way over to router 6 through IGP. Okay, now what we're going to do is on router 2 and router 4, we're going to go ahead and assign a new loopback that's going to be a duplicate address between the two of them. Okay, so we'll say this is loopback 255. We'll say IP address is 150.1.255.255/32. Okay, we already have a network statement in OSPF for this. Interface loopback 255. IP address 151.255.255. And then if we look at the routing table, if we go to router 3, show IP route OSPF, we see we have a route to 150.1.255.255. Now, if we tell it to this, we can see that goes to router 2. Okay, so based on the IGP domain and based on the physical topology, when router 3 sends traffic to this destination, is going to router 2. If we look at this from router 6's perspective, if we telnet to 151, 255, 255, we see this traffic goes to router 4. Okay, so based on the physical topology, 5 and 6 are going to route to 4, 1 and 3 are going to route to 2. Okay, now some of the problems that you could run into if you're running Anycast, you need to make sure that your router IDs for the different protocols are unique, and that the connect source for protocols is not using this Anycast address. Okay, so for example, on router 2 and router 4, what we would need to do now is under our OSPF process, we would need to make sure that this loopback is not the OSPF router ID. So we'd say our router ID is our loopback 0, 150.1.2.2. Okay, we would need to do the same thing under the BGP process. We would say BGP router ID 150.1.2.2. Okay, if we were running MPLS, we would need to say MPLS LDP router ID is loopback 0. Okay, if that Anycast address is chosen, you're going to see that the neighbors will not be able to establish OSPF adjacency. They will not be able to establish LDP or TDP adjacency, nor will they be able to peer via BGP. Okay, if the neighbors are not directly connected and they're not talking to each other by any of those protocols, you can see other inconsistencies in the routing domain. So if we have duplicate router IDs in OSPF, the devices are going to be routing traffic to the wrong destination, possibly. Okay, so destinations that should go to router 4, they may be going to router 2 instead, or vice versa. Okay, so if you're doing this Anycast configuration, make sure you take that into account. Okay, so what we're going to do here on the interfaces, we're going to be running PIM in sparse mode. Okay, so let's get rid of, let me show run include PIM. We're going to take our previous auto RP configuration out. Okay, so we're not announcing ourselves via auto RP. On router 4, we'll take out our BSR configuration. No IPPM BSR candidate, no IPPM RP candidate. Okay, then we're going to run sparse mode on the interfaces. Okay, so on loopback 255, we'll say PIM sparse mode. On the frame relay, on the Ethernet, etc. Okay, so we're moving from our dense network we had before back to our sparse network. Okay, because only sparse PIM requires the rendezvous points. Dense mode does not. ATM, sparse mode, on router 2, on the ATM and Ethernet, and on router 5, on Ethernet 01 and serial 00, and router 6 over to router 5. Okay, so we should have PIM adjacencies end to end here. If we take a look on router 5, show IP PIN neighbors, we should be adjacent with 6 and 4. Okay, which we are. If we look on 4, we should be adjacent with 2 and 5. And if we look at 1, show IP PIM neighbors, we should be adjacent with 3 and 2, which we are. Okay, so now everywhere we have our PIM adjacencies. Now we need to do our RP assignments. We could do this either via bootstrap router, we could do it via auto RP, or we could do it statically. Okay, so what we'll do here, everywhere we'll go ahead and just configure statically that that is the RP address. We'll say IP PIM RP address, RP-address 151, 255, 255. This is the Anycast address. Okay, so the assignment method is independent of the Anycast configuration. Okay, we can assign this however we want. We just need to make sure that everyone consistently knows this is the rendezvous point address. Okay, so if we look at the mappings here, if we say show IPPM RP mappings, we can see statically we know this is the rendezvous point. Okay, we can see BSR is still there. It's going to expire within a minute though. If we look on router 3, show IPPM RP mappings, we can see statically we have the Anycast address. Okay, so if we go ahead and send traffic into the network, so if we go to router 7, we'll say ping 224 5.5.5, whatever random address. Okay, we'll give it a high repeat count. Interface is going out fast Ethernet 00 or 03, coming from 10.137.7. Okay, so router 3 should receive this. If we show IP M route 224.555, okay, we have this the S, G entry for it. We should have sent a unicast register message up to the rendezvous point. In our case, the rendezvous point is going to be router 2. So if we get to router 2 and say show IP M route 224.555, we can see we have this message installed. Okay, the S, G entry. Now, in order to communicate this over to router 4, we're going to have to be running MSTP. If we say show IP MSTP peers, we can see we're still connected to router 4. We should have sent a source active message about 10.137.7, 224.555 over to router 4. So if we show IP MSTP SA cache, we can see we have that entry. Okay, so the key for Anycast is that between the Anycast RPs, we must be running multicast source distribution protocol. We have to run MSTP. Okay, otherwise, when a register message is received at a rendezvous point, it cannot communicate to the other Anycast RPs that the sources are in the network. If we go to the final destination, we'll say IP IGMP join 224.555. This join message should be propagated up to router 4. We say show IPM route 224.555. We see we have both the star G entry, which says go out the serial interface towards the client, and we have the S, G entry. You see the source is reachable out via router 2. The destination is out the serial interface towards router 5. If we go to the last hop, if we look at router 6 and debug IPM packet, we should see the packets coming in gigabit 00 and being forwarded out gigabit 01. Okay, so now what we'll see with the Anycast configuration, if one of these rendezvous points happens to go down, if we go to router 2 and on loopback 255, we'll shut this down. That's going to withdraw our advertisement from the IGP domain. If we go to router 3 now and we telnet to 151, 255, 255, now we'd be sending our messages to router 4. Okay, so it immediately fails over, so any new register messages are now going to go to router 4 instead of router 2. Okay, any questions on Anycast RP? Okay, so the concept here is pretty straightforward with Anycast. We're just using a duplicate address, a duplicate unicast address, in order to load balance the traffic between rendezvous points. Okay, but configuring Anycast RP assumes that we know how MSDP works and that we can distribute this information through the IGP domain without breaking connectivity. Okay, so anytime you have the possibility of duplicate addresses, you need to take that into account. So changing router IDs, that type of stuff, to make sure that you don't have duplicate traffic throughout the network. Okay, now I want to finish up multicast before we break for lunch. So let's go ahead and just take a quick 5-minute break here. When we get back, we're going to talk about source-specific multicast and MPLS VPN support for multicast, where the configuration is going to be really straightforward. It's basically going to be just one command on the provider edge, and then one command on each of the provider routers. Okay, so let's start back in about 5 minutes, and then we will finish up with multicast. Okay, so the last topic we're going to take a look at today in multicast is supporting multicast inside of MPLS VPN access. Okay, so what we're going to see, we're going to build a basic MPLS VPN to connect router 7 and router 8, but inside this VPN, these neighbors want to send multicast traffic through the service provider core. Okay, now there's a couple different solutions that we have for providing multicast inside of MPLS VPNs. Some of the stuff is still under consideration on the standards track, so there are some other ideas that are out there that haven't been implemented yet. The solution that we're going to be looking at is basically a hack to try to get multicast to transit over MPLS. And we're going to see that as the traffic is moving throughout the service provider network, it's not actually MPLS label switched. Okay, so it's going to be regular IP version 4 unicast routed traffic. Well, technically not unicast. It's going to be multicast routed traffic as it goes through the service provider core. Okay, the way we're doing this is basically by tunneling multicast inside of GRE between the provider edge routers. Okay, so if we take a look at the diagram we're going to have here, we have a MPLS VPN that's running between router 7 and router 8. Okay, router 3 and router 6, these are the provider edge routers. Now, additionally, if we did not want to involve the service provider in multicast routing at all, what we could do is just between router 7 and router 8, we could just go ahead and build a GRE tunnel between these two neighbors. Okay, so we could build a tunnel, then inside of this tunnel, we could run multicast routing, and then just not worry about what's going on inside the service provider network at all. Now, the disadvantage of this from the client's perspective is that if there's a lot of sites on the MPLS VPN, then we would have to configure a lot of tunnels. So we basically suffer from that full mesh where we have n times n-1/2. Okay, so same thing with like RSVP tunnels. Manually, we run into that scalability issue. If we use manual GRE, same type of thing here. Okay, we'd have to provision them as fully meshed, or do some type of hub and spoke design that may be suboptimal from a routing perspective. And now, multicast support for MPLS VPNs is basically going to use the same logic here, where we are tunneling the traffic inside of GRE, but the difference is that the GRE tunnel is going to have a destination address that is a multicast address. Okay, so when we enable this functionality, the provider edge routers are automatically going to negotiate the GRE tunnels without any of our manual configuration. Okay, some of the considerations for this, if you look at the documentation, it says that it does not support, slide here. If you look at the documentation, it says that it does not support inter-AS configuration. The reason why is that the multicast, we call this feature multicast data trees, MDT, for MPLS VPNs. The multicast data tree peers, they must be MPLS, or not MPLS, they must be multi-protocol BGP peers. Okay, so in this case, between router 3 and router 6, it's pretty straightforward because they normally would be multi-protocol BGP peers anyways in order to advertise the VPN labels between sites. Now, if we were doing this with inter-AS multicast MPLS, the problem that we would run into is the only inter-AS design that works is the multi-hop VPN v4 exchange, where if router 3 and router 6 were in different autonomous systems, they would still have to be directly peering multi-protocol BGP. If we did the back-to-back VRF exchange, that would not work. And if we did multicast, or not multicast, if we did multi-protocol BGP peering between router 2 and 4, that setup would not work. That's with the current implementation of doing the MDT configuration under the VRF. There is a newer feature that's coming out that defines a new address family that is the VPN4 multicast address family, but that is not supported in the versions that we're dealing with. It's only on 12OS on the GSRs and I believe it may be on the 7200 VXRs. But for our case, we're not going to be dealing with that because it's not supported in our versions. Okay, now when you do this configuration, the peering address for multi-protocol BGP must be running PIM on it. Okay, so between router 3 and 6, if we're peering with their loopback interfaces, we need to make sure that PIM is running on that interface as well. Okay, so there's effectively going to be two different multicast domains that we're running. Inside the provider network, we're going to be running regular multicast routing. Okay, we could be running sparse mode, we could be running dense mode. And inside the VRF, we are going to be running VRF-aware PIM between the provider edge and the customer edge. Okay, so in this example, router 3 and router 6, they're going to have two different multicast routing tables. They're going to have the global multicast routing table, and they're going to have the VRF multicast routing table. Okay, so let's go ahead and take a look at the command line. And the first thing we're going to do is going to set up the basic MPLS VPN between these neighbors. Okay, so the first thing we want to do is enable MPLS in the transit path. Then we're going to peer multi-protocol BGP between router 3 and router 6. Then we're going to run our PE to CE protocol and perform our redistribution. Okay, so on router 3 here, we're going to say MPLS label protocol, we'll run LDP. Then on serial 1, 2, we're going to run MPLS. Okay, on router 1, same thing, we're going to run LDP. We're going to run it on the serial over to router 3, and we're going to run it on the ATM to router 2. Okay, router 2, we're running MPLS on the ATM, and then our Ethernet over to router 4. On router 4, we're running MPLS with router 5, and we're running it with router 2. And on router 5, we'll run it with 4 and 6. And lastly, on 6, we'll run it with 5. On gigabit 00, MPLS IP. Okay, so now that we have our basic MPLS network set up, what we want to do is make sure that we have a label switch path between the loopbacks of router 3 and router 6. Okay, because this is going to be the next hop address for our MPLS VPN, we need to make sure that we have a label switch path between these neighbors. If we say show MPLS forwarding table, how do I get to router 3's loopback? Okay, we see we do have a tag for that. If we trace the destination, we'll trace to router 3. We'll source the packet from our loopback. Okay, we should see it being label switched in the path. Okay, which it is. We see 5 and 4, it's label switched. It's not label switched out to router 2. So let's take a look on router 4. Say show MPLS forwarding table for 150.1.3.3. It says it's untagged as it's going out to router 3. As it's going out to router 2. Okay, so this untagged, this is a breakage in the end-to-end label switch path. Okay, so if we set up our VPN right now, we would have the routes, but we would not have reachability. Okay, so again, you need to make sure that you're checking that your transport label is successful end-to-end before you start involving your underlying VPN label. Okay, so first thing we want to do, we need to make sure that router 2 and router 4 are adjacent via LDP here. So let's say show MPLS LDP neighbors. Okay, we can see we're adjacent with router 5, but we're not adjacent with router 2. Okay, if we look at router 4, it says that our LDP identifier is 150.1, 255, 255. It says for our TCP connection over to router 5, it came from router 5's loopback. It went to 150.1, 255, 255 on us. Okay, so the Anycast RP configuration we had, it interfered with our our MPLS domain. Router 4 and router 2 are choosing the same router ID for LDP. So what we need to do here on router 4, we need to say that the LDP router ID is our loopback 0. We need to make sure that it is not that Anycast address. Okay, same thing on router 2. MPLS LDP router ID is loopback 0. Okay, so on router 4, we'll go ahead and say clear MPLS LDP neighbors. And if we show MPLS LDP neighbors, we should see, we have adjacency with 5. Let me make sure we should have connectivity to router 2. Okay, we do. Show IP OSPF neighbors. Okay, we are adjacent with 2. Show IP route OSPF. Okay, we have the routes through router 2. Okay, MPLS is on the interface. MPLS on the interface here. Show MPLS LDP neighbors. We see we're adjacent with 1, but we're not adjacent with 2, or we're not adjacent with 4. Okay, so at this point, let's go ahead and debug IP packets, and let's see if the LDP information is getting between router 2 and router 4. Okay, so let me save my configs on both of these before I do this debug. And I'm going to say debug IP packet detail. Okay, really I should probably log this to the buffer, but I'm just going to go for it here. Okay, we can see going out to ATM, we have UDP 646 traffic. This is LDP. It's going out to ATM, and it is going out the Ethernet as well. Okay, we didn't see it come in the Ethernet. Now, one of the ways we can filter this a little bit, let's say access list 100. We're going to permit UDP traffic that is port 646. And we're going to permit TCP traffic that is 646. Okay, so now when we debug, we'll say do debug IP packet detail, but we'll filter it through access list 100. So we're looking at just LDP traffic we want to debug. Okay, so if we look at this on the Ethernet, let me undebug here. If we look at the traffic that's coming in the Ethernet, we can see the source address is 150.1, 255, 255. It's a TCP SYN packet. This is router 4 attempting to set up the TCP session for LDP. But we can see where it is coming from. It's coming from that Anycast RP address. So even though we changed the router ID on router 4, we can see it's still trying to source the traffic from that loopback. Okay, so if you do the configuration like this in the wrong order, you can see it'll be really stubborn. It doesn't want to get rid of that address. Okay, so on router 4, let's go ahead and disable LDP on the interfaces, and then we'll bring it back. So we'll say no MPLS IP. Okay, LDP is disabled. Then we'll go back again, MPLS IP. Okay, now we see we have adjacency with 2 and 5. Show MPLS LDP neighbors. And now if we look at the forwarding table, show MPLS forwarding table, how do we get to 151.33? And we can see it is label switched. So if we go back to router 6 and we trace again, we can see it is an end-to-end label switch path. So we can see it gets to router 1. Router 1 is performing penultimate hot popping, sending the unlabeled IP packet to router 3. Okay, so again, unless you test this stuff as you're building it, then you're going to just introduce a lot of troubleshooting headaches. Because if we built the end-to-end MPLS VPN, and then we would have seen that router 7 or router 8 would not have had connectivity. And at that point, there's too many variables that are in there that could be wrong. So as you're building it, you need to troubleshoot it. Okay, so build the basic MPLS transit network. Make sure the label switch path is end-to-end between the addresses. Okay, once you've gotten that, then you can go ahead and establish VPN peers and do your PE to CE routing stuff. Okay, so on router 6 here, we'll go ahead and run BGP 100. We're going to peer with neighbor 151.33 remote AS 100. Okay, under the VPN family, we'll go ahead and activate them. Okay, same thing on router 3. Router BGP 100, neighbor router 6. This is coming from my loopback. We'll activate them under VPN. And router 6, we need to make sure that's coming from the loopback as well. Okay, from 6 to 3. Okay, so at this point, we should have our basic VPN peering. Okay, we can see the adjacency is up. So we'll go ahead and run our PE to CE routing. We'll say, actually, we have default routes on router 7 and router 8. So let's go ahead and just redistribute those segments into BGP. We don't necessarily need to run a PE to CE protocol here. So we'll say, we'll go ahead and create a VRF. We'll say IP VRF 1, route descriptor 11, route target both 11. Okay, so real basic config for the VRF. It will apply this VRF to the customer edge. It will take that IGMP stuff off. We'll say under BGP, address family IPv4 VRF1 redistributed connected. Okay, same thing on router 3 now. We'll say IPVRF1, route distinguisher is 11, both route targets are 11. Okay, on the customer edge, we'll say IPVRF forwarding 1. And under BGP, address family IP version 4, our VRF name is 1, redistributed connected. Okay, so we can see we're originating our local segment, and we're learning that advertisement from router 6. Okay, so if we go to the customer edge, we have static default routes configured here. We should be able to ping over. We're getting ICMP unreachable now. Let me make sure, can we ping 37.7? Okay, we can. Okay, router 3 is sending router 7 ICMP unreachable. Let's say show IP route here. Okay, so statically we'll get to router 3. Let's take a look at router 6, make sure it has the BGP routes. Show IP BGP, VPN v4 all. Okay, they're in the BGP table. Let's make sure they're in the VRF table. So show IP route VRF1. Okay, they're in there on router 6. Show IP route VRF1. They're in there on router 3, 17 seconds. Maybe it was just converging. Let's try again. Okay, now we have reachability. Okay, so we see the basic MPLS VPN configuration is working. Okay, now inside of AS100, we already have our multicast domain built. Okay, so we have PIM running on all the transit links between 3 to 1, 1 to 2, 2 to 4, 4 to 5, and 5 to 6. Okay, we saw that before with our Anycast RP. Okay, now what we're going to do is inside the VRF on router 3 and router 6, we're going to define a source-specific multicast address that is going to be the destination for the GRE tunnel. And now technically we don't have to use a source-specific multicast address, but the reason why it is used is that we can form specific tunnels between individual provider edge sites. Okay, so let's take a look at the diagram here. Okay, so we can see we have router 7 is in site 1, router 8 is in site 1 for the VRF. Okay, let's say that we have somewhere else in the network, let's say that on router 4, we have another VRF site here. Okay, site 1. Now let's say inside site 1, we have a multicast server that is sending traffic. The client is located on router 8. Okay, router 7 does not want this multicast address. Only router 8 wants it. As traffic goes into the service provider network, it is going to be tunneled inside GRE. The destination address is going to be a multicast address. Now, if we use a regular multicast address, so a non-source specific address, anything like 224, whatever. Okay, for non-source specific addresses, when a client sends a join, it can only send a star, comma, G join. Okay, so previously what we saw with basic multicast configuration, router 8 was saying IP IGMP join and then a group. When it was initiating that join into PIM, actually into IGMP with IGMP version 2, it is saying, I want to receive traffic for this group. I don't care where it is coming from. Okay, with IGMP version 3, we have a new specification that allows us to send a specific S, G join. So instead of saying, I want to join group 224.123, with source-specific multicast, we can say, I want to join group 232.123, but specifically from the source 10.1.1.1. Okay, so when we send our join message out, we're going to say, I want 10.1.1.1 going to 232.123. Okay, that's the specific group I want. So we're saying not only this destination, but also this source. Okay, this is a functionality of IGMP version 3. Okay, now with source-specific multicast, one of the implications of this is that we do not require rendezvous points. The reason why is that there are no shared trees inside source-specific multicast. Okay, remember the issue that we're trying to address with using a rendezvous point in sparse mode. Okay, the rendezvous point is the meeting place for two things. It's the meeting place where the source registers with the rendezvous point, and the destination is sending its star, comma, G join. So when the traffic is moving through the rendezvous point, it's a shared tree because it goes from the source to the rendezvous point, and then from the rendezvous point it merges it with the destination. With source-specific multicast, the first hop router, who is the designated router, it knows already exactly what the source that the host is requesting. So instead of sending the join for 10.1.1.1 up towards the rendezvous point, it sends it up the shortest path tree towards 10.1.1.1. Okay, so with source-specific multicast, we configure PIM sparse mode everywhere, but you do not need rendezvous point assignments. There's actually only one command that you need in iOS to enable source-specific multicast. In global configuration, you say IPSSM default. What this means is that you will allow source-specific joins for groups in the 232.0.0.0/8 range. Okay, per the RFC, it says that you can only, inside 232, you can only send source-specific joins, and outside of 232, you cannot send source-specific joins. Okay, so it's saying that is the source-specific range. You have to use that range if you want to send a source, group join. Now, the way this is going to apply to multicast MPLS VPNs is that when we build the GRE tunnel between the provider edge routers, the provider edges can say, I want the tunnel specifically from this source. Okay, so if we look at the diagram here, when we are setting up the MPLS VPN, what do we already have running between router 4 and 6, router 3 and 6, and router 3 and 4? We're going to have multi-protocol BGP running between these neighbors. We have multi-protocol BGP because we are exchanging our VPN v4 updates. Okay, let's say that they're coming from the loopback addresses of the router. So when we're doing our BGP peerings, we're peering with the loopback addresses. Okay, router 6 now knows that router 8 wants multicast traffic from this server 1 on router 4. When router 6 sends the join, it's going to say into the transit network that I want the traffic for 150.1.4.4, comma 232.123. So router 6 is sending a join. It's saying, I want the traffic that is coming from 150.1.4.4 that is going to 232.1.2.3. A 232.1.2.3, that's some arbitrary address that we are going to define for the VRF. Okay, so what this allows us to do is that when router 4 is sending the multicast traffic into the service provider network, we can send a specific feed towards that group address, and only router 6 is going to receive it instead of both router 3 and router 6 receiving it. If we did manually specify GRE tunnels, what would happen is that every time we send a multicast packet out to the service provider network, we would be sending it out every single tunnel. If we have 100 sites in the VPN and there's only a client in one of those sites, that's going to be that's not going to be an optimal design, because we're sending the packet out 100 times. We really only need to send it out once, out one of the tunnels. Okay, so the multicast over, or the MPLS VPN over the multicast is going to optimize this by using source-specific group addresses between the provider edge routers. Technically, you don't have to use the source-specific groups if you don't want to. You could define any group that you want. But in a practical implementation, you would want to do that to minimize the amount of flooding that is necessary between the provider edge sites. The configuration is very straightforward. It's only going to be one command under the VRF. We use the MDT default command. That is going to define our source-specific group. There's also another option. We can say MDT data, and it's going to give us a range of addresses. What this is going to be used for is that if we want to set up different tunnels on a per flow basis, we can use different source-specific addresses. The reason that we would want to do this is, like I was saying, to reduce the flooding throughout the network. So if we want to send the traffic only to site 1 instead of to site 1, 2, 3, and 4, we could use a separate source, group pair. Okay, now in our case, we already have the multicast set up in the transit path. Okay, so everyone is running multicast. So the only thing in the provider network that we're going to need to do is add support for source-specific multicast. Okay, then on router 3 and router 6, we're going to run the multicast data tree instance inside the VRF, and we are going to run PIM with the customer edge. So we're going to run VRF aware PIM with the customer edge. we're running regular PIM inside the transit network. And to build the tunnels, we're going to be sending source-specific multicast joins. Okay, it's going to be automatic once we configure the group address in there. Okay, so in the transit network, first thing we're going to do is in global configuration, we'll say IPPIM SSM default. Okay, this is enabling us to accept source-specific joins. So we'll do this everywhere in the transit path, IPPIM SSM default. Okay, multicast routing is already on, PIM is already on the interfaces. And on router 6. Okay, now on the provider edge, we are going to be running VRF-aware PIM with the customer edge. Okay, so let's say inside this VRF, we're just going to run PIM in dense mode. Okay, we could go over to router 8. We'll say IP multicast routing. Okay, this is the customer edge. Then on the interface, we'll just say IP PIM dense mode. Okay, so normal dense configuration. Let's say we'll enable it on our loopbacks as well, IP PIM dense. Okay, same thing on the other customer edge, router 7. IP multicast routing. On the loopback, IP PIM dense. And on the link to the provider edge, IP PIM dense. Okay, now on the provider edge, which is router 3 and router 6, we're going to enable PIM for this VRF instance. So we're going to say we're running multicast routing. We already have that globally configured, but we're also going to run multicast routing for VRF1. If we were doing sparse mode inside this VRF, we have other VRF-aware PIM commands in order to do our normal multicast configuration. So we could say, for example, IPPIM RP address 1.2.3.4, but this is inside VRF1. So for the VRF1 instance of multicast routing, that is the rendezvous point address, where in our global multicast routing, we have a different address. Okay, also, when we do our verification, we'll say show IPPIM VRF1 neighbors instead of show IPPIM neighbors. Okay, so on Ethernet 00, which is our customer edge facing interface, we just say IPPIM dense. Okay, so we can see we have a PIM adjacency inside VRF1. So we'll say show IPPIM VRF1 neighbors. And likewise on router 6, we'll say IP multicast routing, but this is going to be inside of VRF1. Then on the customer-facing interface, IPPIM dense mode. Okay, we can see the neighbor comes up if we say show IPPIM VRF1 neighbor. We see we're adjacent with router 8. Okay, so now between router 3 and router 6, we're going to establish a GRE tunnel automatically inside the VRF. So under the VRF, we'll say we want to create a multicast data tree. The default address we're going to use, we'll say, is 232.1.2.3. And we'll do the same thing on router 3 here. So IPVRF1, MDT default, 232.1.2.3. Actually, I skipped a step. It's a real easy step to overlook. We need to make sure PIM is on the loopback interface here, because this is our peering address. IPPIM sparse mode needs to be on here. So on the loopbacks of 3 and 6, IPPIM sparse mode. Okay, so what we can see the message, once we enable PIM on the loopback, we have a new PIM adjacency. it says it's over interface tunnel 0. Router 3 is adjacent with us over tunnel 0. If we say show IP PIM VRF1 neighbor, we are adjacent with router 8, who's the customer edge, and we're adjacent with router 3 over our tunnel interface. Okay, if we look at this tunnel, if we say show interface tunnel 0, it's a regular GRE tunnel, but the destination is going to be a multicast address. Okay, it says the tunnel protocol is GRE, but we're transporting it over multicast instead of unicast. Okay, the source is my loopback. The destination is that MDT address that we defined, 232.1.2.3. Now, if we go to the service provider network and we look in the transit path, like let's say we go to router 4 and we show IP mroute, what we're going to see is two different S, G entries. We're going to see one coming from the loopback of 3 going to this multicast address, and one coming from the loopback of 6 going to that address. So if we say show IP mroute 232.1.2.3, we see we have those two entries. If we look in the flags, we can see lowercase s. It says this is a source-specific group, 232.1.2.3. So router 6 sent a source-specific join towards the multi-protocol BGP address for that VRF, which is 150.1.3.3. Likewise, router 3 sent a source-specific join to 150.1.6.6, which is the address that router 3 is peering with in multi-protocol BGP. Okay, now if we went to router 8, let's say we go to our loopback, we'll say IP IGMP join 224.1.1.1. If we go to router 7 and we ping 224.1.1.1, actually let's do extended ping, 224.1.1.1, going out fast Ethernet 03. Source is 10.137.7. We see we're getting replies from router 8. Now, if we look in the transit path, if we go to router 4, for example, and on these interfaces, let's say no IP route cache, no IP route cache, and I'm going to create a new access list. I'll say access list 101, permit GRE any. A GRE is the protocol that we're going to debug. So I'm going to say debug IP packet detail through access list 101. This is not going to be, we can't debug this through IP packets. This would be a debug IPM packet. This, I don't believe, we can't put it, let's put it through access list 101. So we can see this is protocol 47. 47 is the IP protocol number for GRE. This traffic is coming from router 3. It's going to 232.1.2.3. Now we can see, since we can debug this as an IP packet, this traffic is not label switched as it's going through the MPLS network. So what this is allowing us to do is just tunnel this inside of GRE. This is not true multicast label switching, because you cannot bind a label for a multicast destination. At least in the current implementations. There are some work on multi-point labels to bind multicast destinations, but as of these versions, it does not support it. Okay, so basically, we're just automatically creating a GRE tunnel between the endpoints. So the configuration that relates specifically to this, if we look at the VRF, the only thing you need to say inside the VRF is that this is the group address you want to use. Okay, we're running multicast routing for this VRF. Then we have PIM on our interfaces. We have PIM on our global interfaces, and then we have PIM on our VRF interfaces. If we go under the VRF here, you also have this MDT data option, which says that we're going to use 232.1.2.10. Let's say 232.10.10.0.0.0.255. If the bandwidth of a particular flow goes above 100 kilobits per second. Okay, so what this means, if I have a multicast traffic flow and it goes above 100 kilobits per second, instead of using the default group address which we have, which is 232.1.2.3, we're going to create a separate tunnel and send it out to that destination. Okay, so not every provider edge router is going to receive it unless they're specifically asking for it. Okay, so let's go ahead. Let me set this threshold a little bit lower. Let's say 10 kilobits per second. And on router 7, let me try this ping again. Actually, this would be on router 8. Yeah, router 7, let me go ahead and join a group. Say IP IGMP join 225.555. Okay, on router 8, okay, there's a question here. If multiple streams are within the limit, would you still use the default MDT? Yes. Okay, so it's on a per flow basis. So if an individual flow goes above the threshold, then it's going to set up a new tunnel for that individual flow. Okay, so let's see if we can get past this threshold on router 8. Let's ping 225.555. Send a lot of packets. Datagram size we'll say is 1400 bytes. Timeout is 0, so we're just going to flood all the traffic out the interface. And the commands, yes, we're sending it out fast Ethernet 06. Source is 10.168.8. And actually, I needed that command on the other side too. Let me see. Show run include MDT. So on router 3 under the VRF, we'll do the same thing. And to verify this, if the tunnel is coming up, we want to look at the show IP PIM MDT and the show IP PIM MDT BGP outputs. Okay, this tells us who our peer is on the other side of the link. So on, let's take a look at that on router 4, that debug IP mPacket list 101. Let's see if that traffic is going through. So it is going through, but it's not very fast. Let me try setting the threshold down some more. Show IP PIM MDT. Okay, so we still only have that one tunnel interface. IPVRF 1. MDT data, we'll say is 232.10.10.0.0.0.255. Now, you could really use the entire range here. It doesn't matter, because the group is always unique because it is a source comma group entry. So if some other VRF is overlapping, it doesn't matter because their source address is going to be unique. Okay, so if they're using 232.123 and you're using 232.123, it doesn't matter because their source address is going to be different than your source address. Let's say the threshold is 1 kilobit per second. IPVRF 1. Okay, so we still only have one tunnel interface. Let's see in the transit path what the groups are that are created. Show IP mroute include 232. Okay, so we still only have that one group. So probably the switch, let me see, is it done sending? No, it's still sending. But really, those are pretty much the only two options that you have on the provider edge. So you just define what the main group address is that you're going to use, and then if you wanted to separate the tunnels based on, you can. There's another option there, IPVRF1, MDT data 232. You could say based on this access list. So you could say if it's this specific group or it's coming from this source, then you could split that off into a different tunnel. Okay, but the key here really is to make sure that you have inside your service provider network that you have multicast functioning correctly. If you want to use source-specific groups here, you would need to go to everybody in the transit path and then say IPM SSM default. Okay, you could technically change the source-specific group range, but the RFC says that only the 232 range should be used. Okay, then on the provider edge, you're going to run multicast inside the VRF. So you say IP multicast routing for that VRF. Run PIM with the customer edge, then enable this multicast data tree inside the, or multicast distribution tree inside the VRF. Okay, there's a question here. Is the RPF check performed against the tunnel interfaces? Yes, it is. Okay, so when the traffic is received on router 5 from router 6, it's going to do an RPF lookup on the loopback of router 6. Okay, so when this traffic comes in here, it's going to be saying, do I have a route to router 6's loopback? If the route to router 6's loopback is out Ethernet 0/1, then the RPF check is going to pass. Okay, so if we have a link between router 1 and 5 there, and the unicast route is out that link, when the traffic goes down through the network, if it goes this way and router 1 receives it in the ATM, then the traffic would be dropped. Okay, so this isn't a problem that's specific to the MPLS VPN. It's just based on this would be a failure of the multicast traffic flow through the service provider network. Okay, so either you would need to enable PIM on that link between router 1 and 5, or on router 1 you could do like a static multicast route to say that it's okay for it to come in the ATM interface. Okay, there's a question here. So PIM dense mode between the PE and the CE, and PIM sparse mode between the PE and the PE. Technically, the PIM mode doesn't matter. You could run dense mode inside of the service provider network. Just typically, that's not a design that's used in the real world, because you don't want to be flooding your multicast traffic everywhere. You want to send it specifically to the people that want to get it. Okay, since it is source specific, you don't even need the rendezvous points. It's going to be, the endpoints are going to be joining specifically to the groups that they want and the sources that they want. Okay, likewise inside of the customer edge, the customer network could be running sparse mode, and if you were running sparse mode, then you would have to do the RP assignment inside of the VRF. Okay, so on router 6, for example, you could say IPPIM VRF1 RP address, and then the RP address is router 8. Or you could run AutoRP or BSR inside that VRF. Okay, so it's the same exact functionality as regular PIM. Just when you go to configure it, you add the VRF keyword after the PIM command. Okay, so that's going to do it for multicast for the day. So let's go ahead and break for lunch now. We'll go ahead and start back in an hour. And then this afternoon, I'm going to talk about layer 2 VPNs very quickly. We'll take a look at one of the examples for layer 2 VPNs. Then we'll talk about some strategy and where to go from here with your preparation. Okay, so let's start back at about 30 minutes after, and then we'll go ahead and continue from there.
Okay, let's go ahead and get started with troubleshooting here. Pretty much to the end of the class here, so you guys have seen a lot of troubleshooting this week, to say the least. And that's kind of the advantage of the of doing the class live on the equipment, as opposed to let me get back to the beginning with the slides here real quick. As opposed to just showing you, slides all week. So it's a lot better for everybody. If we do it live on the equipment, you see the problems that we run into, and that way, you get an idea of what you can expect when you start working on these types of configurations. Okay. So let's go to the first slide here. I'm going to mention this really quick. It's not an issue. You could run through all the labs in the workbook and you will never see an issue where you need to change the MTU. Okay? The MTU issue was a big problem in previous versions of the iOS. Basically, the problem was that the MTU for IP is 1,500 bytes. Once we add on the additional an additional label or 2 labels, we're going to add on 4 bytes for each one. So that would mean essentially your packet is larger than the WHAT consent. It's not an issue today in the networks you deal with today. For one thing, is you can't set the MPLS MTU larger than the interface's MTU. 1,500 bytes. It won't allow you. It used to allow you to do that. Another thing is that Cisco iOS can support frames larger than 1,500 bytes. Okay, not all platforms, as you guys know, support larger frames, and those are platforms like the 2500s. But the 2600s, you can do like ISL trunking, so you can see that it's dealing with frames that are larger than the standard Ethernet maximum of 1,500 bytes for the MTU there. So this isn't an issue today. If you're working in an older network, you may always remember that your edge MTU will be normally smaller than your core MTU. But in today's networks, you really don't see a lot of people adjusting the MTU. Okay, it's really not as big of a problem as it used to be, especially with like Ethernet. As far as Ethernet and the technologies that we deal with today here. Okay, so it isn't a real problem here. If you want to know, what type, not what type, but how big a packet could possibly be, there's a really good book out there. It is kind of basic. I should say it's one of those introduction to routing books. There's one called MPLS Fundamentals, and I believe in that book there's a few scenarios that they run through to show you exactly what the exactly how big the packet would be. If it's pretty simple to figure out. If you got if you run the MPLS VPNs, you're going to have two labels. So you're going to have the largest frame you're going to possibly have, or packet you're going to possibly have, is 1508. But you could get into situations where you're doing carrier supporting carrier and so forth there. But with standard MPLS, you're going to have the maximum is going to be 1504. With traffic engineering, 1504, because traffic engineering is one label on there. Okay. The different terminology here. The different terminology that everybody needs to be familiar with for us to move through this troubleshooting here. The RIB, that is the routing table. When you hear the term the RIB, that is the routing table here. So how do you view it? Show IP route. The FIB, okay, that is the forwarding information base. That is the CEF table. Okay, essentially you'll see packets are basically, the router makes a decision, and then CEF derives where to forward that packet based off of the RIB. The routers don't really route packets much anymore. Most of them are switched using CEF. Okay, so they're not switched like as in a layer 2 perspective, but they don't go to the processor anymore here. Well, I guess I could say they haven't gone in a long time, but CEF really improves this performance here. So the FIB, when we're talking about the FIB, we're talking about CEF. There's something called the LIB, Label Information Base. This shows you all the labels you are learning. So this shows you all the labels that you are learning from your neighbors, your MPLS neighbors here. How do you view this? Show MPLS label bindings. This will show you additional labels that you may have, labels that you'll use in case of an outage in the case of an outage in the network there. Sure, if you read a little bit about MPLS, you hear terminology like conservative and liberal talking about how they store labels. This will show you the labels that we are storing, that the router is storing, that it may not be using. The idea is that it's just like the routing table. You don't really want to do a conservative. If you did a conservative format for the routing table, let's say if every route I did not use was thrown away, OSPF didn't store any alternate routes, RIP didn't store any alternate routes, BGP didn't store any alternate routes. That would mean whenever we had a route that is removed from the routing table due to some reachability issue, that would mean that you would have to request or find out from other routers what the alternate route is. So it's the same logic with the LIB. You're going to store this information, so it is synonymous with like OSPF, the OSPF database. All right, the FIB. This is essentially what you're actually forwarding. Okay, this is synonymous with your routing table. Okay, so how do you view this? Show MPLS forwarding. This is the thing you're going to be looking at the most. Show MPLS label bindings, not very often. Okay, you may want to know what the alternate path you're going to take, or are you learning labels from a neighbor but you're not using them? You can view them through here. Okay. 2 domains we'll deal with in troubleshooting. One is the control and one is the forwarding. Okay, your control is essentially the communication between the devices. Your forwarding is the actual forwarding of the packets here. Most of your troubleshooting will relate to the forwarding plane, not the control plane. The control plane, these are the configurations, you know, when we're getting on there and verifying that we're learning LDP, or that we have traffic engineering configured, or that we have we're learning labels through BGP or so forth there. So, or we're just actually getting the routing information. So that's the control plane. The forwarding plane is the actual forwarding of the packets. So if you can, you know, so if you have reachability to part of the network, you know, normally you're going to be doing some sort of some forwarding plane troubleshooting. Commonly, you're going to verify your control plane as you apply your configuration. Right. For basic troubleshooting purposes, depending on what we're looking for here, if it's an IP to IP packet, we're going to do a show IP SAF or a show IP route. If it's an IP to MPLS packet, we're going to do show IP SAF. Okay. So depending on where the packet, if we're on a P router, that packet, if we're on a pure P router and we're having trouble with reachability across the network, for like an MPLS VPN or something, that's going to be an MPLS to MPLS packet. Okay, if it's a PE router, okay, if it's a PE router, it may be IP to MPLS, or it could be MPLS to IP, depending on, you know, is it inbound or outbound into the MPLS network here. So depending on what the packet is going to determine. It's going to help determine what commands you are going to use for troubleshooting. As a side note, if you do not understand MPLS in depth, means if you do not have if you do not have the level of understanding you need to pass the CCIE lab, if you do not have that level of understanding, troubleshooting is really hard. Okay, troubleshooting is hard enough as it is. But troubleshooting will be extra hard if you really don't understand what's going on. One of the things I like to mention too, I don't have it in the slide here, but as far as terminology, people get mixed up. What is downstream and what is upstream? They throw these terminologies in MPLS because we build 2 label switch paths. A downstream and an upstream. Essentially, you're going to have a label switch path to the downstream and upstream between the source and basically the destination. And the one way to remember this is downstream is near the destination. Upstream is near the source. Some people think it's kind of backwards to think that the label switch path is built downstream to upstream. You build it from the destination out to the you build it out from the destination to the other PE routers. So you build a label switch path in that direction there. But this is the same way unicast routing works. The destination advertises itself out. So the destination advertises itself out, and then once you get down to the edge of the network, you can think of it as the same way as, okay, now the source is going to advertise its route up. So it's kind of like the same thing. They're kind of synonymous with each other. As far as unicast routing and MPLS, it's just that we have 2 totally different paths that we are looking at here. All right. So you always want to remember downstream is at the destination. So if you're at the downstream router, that is the router on the PE. Upstream is towards the source. It just depends on how you're looking at the network, but it's the same basic logic with unicast routing. It's just that we don't have the complexity, the additional complexity we have here. But you could have the same type of issues though, like in routing. You may be able to reach the destination, but the destination may not be able to reach you. Okay, or vice versa there. It's the same thing with MPLS. Just because you cannot reach a destination, it does not mean your packet, just because you cannot ping a destination, it does not mean your packet's not actually making it there. You should go on to that destination, debug IP ICMP, and then make sure see if that packet's even making it to that end. I think we saw that this week once or twice, where we essentially had the label switch path built in one direction, but not in the other direction there. All right, so just remember downstream is the destination. Okay, control plane verification. So verification to verify, we do not have any issues with the control plane. These are the ones we saw this week here. Ensure IPsec is enabled. So that should just say ensure Ceph is enabled on the interface. If you see no IP route cache Ceph, that means Ceph has been disabled. You can also verify this by show IPsec and then the interface. So normally, you're not going to get in there and disable Ceph for an interface. If you do, you're going to break, of course, MPLS. All right, if you do show IPsec or show IPsec summary, it'll tell you if Ceph is disabled. Okay, the next thing to do, once you are sure that Ceph is enabled, and this is a problem you could run into because you are so used to working on routers where Ceph is enabled. Now you get to an environment where either someone has disabled Ceph or Ceph is not enabled by default. Okay, so if you look on the iOS blueprint, some of those routers are 2600s running, I think, like 12.2. So you need to verify that Ceph is enabled. Okay, so don't just assume Ceph is enabled because it's going to create all kinds of problems for you if it's not. All right. The next step we want to do, once we know Ceph is enabled in our network, we want to go ahead and enable LDP on the interfaces. Once we enable LDP on the interfaces, we want to make sure that our protocols match between our neighbors. And let's look at that. Let's look at that real quick here. So we're going to do a show here. We're going to do a show show MPLS LDP discovery. Okay, the discovery command shows us, first of all, what our router ID is, which is going to be important. It also shows us the protocol that we are using, and it shows us that we are transmitting and receiving LDP on this interface. So in this case, it shows the router ID of our neighbor here. This router is running 12.3.14t. Its default is TDP. It's not LDP. I think we saw this yesterday. So the default is TDP, not LDP. So as a standard part of your staging your routers, go in the global config IPsec. More than likely you're not going to be tested on tag switching. Okay, so more than likely you're not going to be tested on tag switching. It's just in older technology that most people have moved to LDP now. You will see a couple examples of it in the workbook, but as a standard practice, what I would do, I would go in the configuration, say IPsec, MPLS, label, protocol, LDP. Just go ahead and put that on. Someplace you may see that you're not going to use LDP, even in today's network, would be like for ATM. You may, like we're running with the LS1010 or our remote router that we have across ATM, we may be running TDP with it. So in that case, you may need to go under the interface, and if you're not sure what it's running, so if you're not sure what protocol it's running, you can go into the interface and you just specify both. That way, once you specify both, it'll try to establish a relationship using both protocols here. Not that it matters much, but the routers will prefer LDP now over TDP if you can configure them both here. Okay, so if for some reason or other you don't know what the device is, let's say you're running MPLS with a backbone device, you don't know what the protocol is, just do both. Okay, show MPLS LDP neighbors. Okay, so this is showing us information about our neighbor relationship we have with R1 here. We also see all the interfaces that are attached to R1. Here, this is the interface we're connected to, and that's the source IP address for R1 here. And you can also see messages received, messages sent. The values are incrementing here as time goes on. Usually it'll get pretty stable. It'll get pretty stable as the network gets, as you finish up your configuration. But it's showing you that our neighbor relationship is established. One thing you're going to want to be aware of, at this level, it's really not going to trip too many people up. Make sure you understand that this is a TCP session. Your access list or your NAT config could affect it could affect your ability to establish a neighbor relationship through LDP. So, just in case you need to figure it out, so you need to put an access list on and figure out what ports to use. What you can do is just put an access list on that logs everything. So, access list 100 permit TCP any log. Okay, and then apply that to the interface. Then you'll see the LDP traffic inbound, and then you'll know what port to use. All right, but you can also just remove the access list off the interface. Some people say, well, how am I going to remember what the ports are? Like I said, just remove the access list on the interface, let them become LDP neighbors, look at the ports that they're using, then go ahead and design your access list. All right, so the two commands for LDP, discovery here, it shows us running on the interface, shows that we are transmitting and receiving. Here we are transmitting LDP and TDP. We can see that we have decided to use LDP here. All right. So if you're not establishing an LDP neighbor relationship, the first thing you're going to do is go onto the routers, do a show MPLS LDP discovery, and find out, look at each side, and then figure out, okay, why am I not able to see each other here? Okay, or why is my neighbor relationship not coming up here? All right. Switch back to the slides here real quick. You can also do a show MPLS interfaces, and it'll show you what's enabled. It'll show you if traffic engineer is enabled for the interface or LDP is enabled for the interface there. Okay, we already talked about check the neighbor adjacency. One of the biggest problems that people have is they do not have reachability to the router ID. So if you do not have reachability to the router ID, your LDP relationship is not going to come up. Make sure that you have reachability to the router ID. If for some reason or another, you don't have routes to each other's loopback, then force your LDP session off of an interface. So that's in the global config. The command MPLS, let me look at it real quick. It's MPLS LDP router ID. Then you specify the interface. There's also an option on the end of it that says force. So the command here, MPLS LDP router ID interface, then force. If you change the router ID after the LDP session is already up, it's not going to come into effect until you drop the connection. You essentially bounce the interface. Somehow break that neighbor relationship there. If you force, it'll interrupt it, and then it'll essentially reset it. So that's the basic idea behind it. So if you need to switch the LDP router ID on the fly, the way to do is use the force option there. Okay, this is very important. Okay, this part about ensuring reachability to these router IDs is very important. It is like the #1 goal that you're going to have is to make sure you have reachability to everybody's router ID. So everybody's loopback, I should say. So everybody's loopback here. Make sure you have reachability to everybody's loopback, because that's how you need to build these label switch paths. Because this can be based off of the loopbacks here. For ATM, if you cannot form an adjacency, what you can do is you can do a show MPLS interfaces, the ATM interface, and then detail, and it'll show you the control VC that you're using. Make sure you're using the appropriate one. If not, you will not.